Okay, let me continue with linear differential equation with constant coefficients. With constant coefficients. We have seen that if you have a differential equation of the form dy f of d operating on y equal x, then its solution is given by y equal complementary function plus particular integral. To find complementary function, we have to find first the auxiliary equation. The roots of the auxiliary equation may be real and different, may be equal, and may be complex. And you know all the three cases, what is the complementary function. And for particular integral, you have seen for e to the power ax, particular integral is e to the power ax upon f of a. You are replacing d by a, provided f of a is not equal to 0. And if f of a is 0, you are using a particular formula, which is e to the power ax upon d minus a whole raised power r equal to x raised power r by factorial r e to the power ax. Similarly, for sine and cos, you are using the formulas. It means you are actually using to find particular integral for different functions is different. This I want to emphasize. So I have shown you e to the power ax, sine, cos, and a polynomial. Now I have told you one more case, that is the product of functions. Say you have a question, say d square plus 8d plus 16 operating on y equal to e to the power minus 3x x cube. See, this is d square plus 8d plus 16 operating on y e to the power minus 3x x cube. See, this is the product of two functions, e to the power ax and v, fd. What is the particular integral? It is e to the power ax. What remains is that you are replacing d by d plus a and operating on v. This is the solution of this particular integral of this. To find auxiliary equation, you have m square plus 8m plus 16 equal to 0, which gives m equal to minus b plus minus under root of b square 4ac to a. So it is minus 4 and minus 4. So it is m plus 4 whole square or d plus 4 whole square. So you have repeated factors. So complementary function is c1 plus c2x e to the power minus 4x. This is the complementary function. Now for particular integral, pi, it is e raised power minus 3x x cube d square plus 8d plus 16. Now this is the product of two functions, e raised power minus 3x as it is. What you have to do, you have to replace d by d plus a. A is minus 3 over here, so it is d minus 3 whole square, a times d minus 3 plus 16, and the rest of function is x cube, and operate on x cube. You see, x cube is a polynomial, so you have to use the binomial expansion. First of all, you have to evaluate this one. This is e raised power minus 3x. This is 1 upon d square minus 6d plus 9 plus 8d minus 24 plus 16 operating on x cube. Or you have particular integral as e raised power minus 3x 1 upon d square minus 6d plus 8d, so it is plus 2d only. Then you have minus 24 plus 16 plus 9. 16 plus 9 is 25. 25 is minus 24, this one. And operate it on what? X cube. Now what is the method? Its part was your e raised power minus 3x. Its part is only that you have to replace d by d plus a. That we have done. Now what remains is this question. X cube by fd. This is a polynomial and this is FD. You have to take lowest degree term out. The lowest degree term is 1, so we don't have to take anything out. So what is the method? You have to take this function into the numerator, which is 1 plus d square plus 2d raised power minus 1 operating on x cube. Fine? This is d square plus 2d plus 1 or 1 plus d square plus 2d. So in the numerator it will be 1 plus d square plus 2d raised power minus 1. This is 1 plus x raised power minus 1. So what is the expansion? 1 minus 2d plus, it is square, d square plus 2d whole square plus its cube. Not plus minus, plus minus plus minus plus cube and so on. You see, and operate it on what? X cube. This is plus so on and operate on x cube. You will differentiate x cube only thrice. So you have to go up to d cube only. So this e raised power minus 3x, 1 into x cube, okay, then d square into x cube, sorry, d square operating on x cube, not into, then plus twice d of x cube, then it is d square whole square, which is d4. You don't need to find, you take d4 because it will be ultimately 0. Then d square plus 2d whole square, so it is 4d square operating on x cube. Then twice ab, 4d cube x cube. Okay, see, a plus b whole square is a square, d raised power 4. You cannot take that. Then 2d whole square, it is 4d square. I have taken that. Then 2ab, 2 into 2, d cube into d is d cube. Sorry, d square into d is d cube operating on x cube. Now what remains is derivative of, power of d square plus 2d whole cube. This is a plus b whole cube. So a cube is d6. b cube is 8 d cube operating on x cube. Rest will be functions of or powers of 4, 5, 6. We don't need to take those. Fine. Let me explain it again. You have x cube only. X cube means polynomial of degree 3. So you can differentiate only up to 3. So I have to take only d cube of 3. D cube of x cube, which is factorial 3, you know that. But then I cannot take d4 because d4 will be 0. That is why I have taken only this term, this term, this term, not this square of this term, because it will be d4. Then it is square, and then product of these two is d cube. I have taken that. D square whole cube is d6. I cannot take that. Then 2d whole cube is a d cube, and rest of will be higher powers of d. We will omit that. So the ultimately particular integral is e raised power minus 3x x cube minus twice derivative. See, derivative of x cube is 3x square. Second derivative is 6x and third derivative is 6. Fourth derivative will be 0. I will use that. X cube, d square of x cube is 6x. Then twice d of x cube, d of x cube. It is 3x square, so it is 3 to 6 x square. Then 4 d square of x, d square is 6x. 6 into 4, 24x. Then d cube, it is 6, 4, 6, 24. Plus d cube, it is 6, 6, 8, 48. Let me explain it again. X cube as it is, then d square, you see, d square of x cube, it is 6x. d of x cube, it is 6. d cube of x, d of x cube is 3x square. d square of x cube, derivative of this once again it is 6x, and d cube of x cube is 6. So I have used these three only. This is d square of x cube. D square of x cube is 6x. So I have written 6x. Then 2 as it is. D of x cube. See, d of x cube is 3x square. 3 into 2 is 6x square. Then 4 is as it is. D square. D square of x cube is 6x. So 6x into 4 is 24x. Then d cube. 4 is as it is. D cube. D cube is 6. 6 into 4 is 24. Then again d cube. It is 8 into 6, 48. Now we can simplify it. This is e to the power minus 3x. X cube plus 6x square minus 6x. Oh, sorry. 24. It is 18x. 18x. You see, you have minus 6x plus 24x. And plus 8, 4, 12, 72. This is the particular integral. And your general solution is CF plus PI. Okay. Let me take one more example. D square plus D plus 1. Let me write it as like this. D square plus 2D plus 1 operating on Y equal e raised power minus x sin x. What I have to do is that you have product of two functions, e to the power minus x and sin x. I will not go to the auxiliary equation. I will not find auxiliary equation because it is very simple. This is d plus 1 whole square, m plus 1 whole square, m is minus 1 and minus 1. So let me write particular integral only. E raised power minus x sin x d square or d plus 1 whole square. See, this is as good as d plus 1 whole square. Now what I have to do, it is nothing but e raised power minus x replacing d by d plus 1. D plus a is minus 1, so d minus 1 plus 1 whole square operating on sin x. Fine? So it is e raised power minus x 1 upon d square sin x. So this means either you have to integrate sin x twice or you have to replace d square by a square minus a square. A is 1, so minus 1. So it is e raised power minus x sin x by minus 1. This is the particular integral. So general solution is CF plus PI. Okay? Let me explain it again. You have product of two functions, e raised power ax into v. V is some other function of x. What you are doing, e to the power ax out. You are replacing d by d plus a is minus 1 here. So d minus 1 plus 1 whole square. 1 and 1 goes and you have to operate it on v. V is x sin x. So this is sin x by d square. Replace. The rule is that sin ax upon d square plus a square, you have to replace d square by minus a square. So d square by minus a square means minus 1. So the solution is this. And final general solution is complementary function plus particular integral. Let me take one more question. D square plus d plus 1 operating on y equal e raised power 2x sin 3x. D square plus d plus 1 operating on y equal e to the power 2x sin of 3x. Now auxiliary equation, you will do it yourself. Okay, particular integral only. E raised power 2x sin 3x upon d square plus d plus 1. Now what you have to do is, this is e raised power 2x, you have to replace d by d plus a. This is d plus 2 whole square. Let me write it over here. E to the power 2x d plus 2 square d plus 2 plus 1 operating on sine 3x. Okay? Whether it is sine or cos, you have to proceed like this. If it's a polynomial, then you have to proceed in another way, as has been done in question 1. Now this is d square plus 4d plus 4 plus d plus 2 plus 1 operating on sine 3x, or this is e raised power 2x 1 upon d square plus 4d plus d, it is 5d, then 4 plus 3 is 7 operating on sine 3x. Now what you have to do, you have to replace d square by minus a square. A is minus 3 here, so minus a square is minus 9. So this is equal to e to the power 2x sine 3x upon minus 9 plus 5d plus 1. Okay? So this is e raised power 2x. This is sine 3x. This is 5d minus 8. What you are doing, and what you have to do is that you have to rationalize it in order to get d square. So let me write 5d plus 8, 5d plus 8. This is e raised power 2x, 5 differentiation of sine 3x plus 8 sine 3x, 25d square minus 64. Okay? A plus b into a minus b. This is equal to e raised power 2x, differentiation of sine 3x, it is 3 times cos. So 3, 5, 15, cos 3x, 8 sine 3x, d square is what? It is, it was minus 9. 25 into 9 is 225. So minus 225 minus 64. So the general solution, particular integral is e raised power 2x, 15 cos 3x, 8 sine 3x divided by 9, 8, 2, minus 2, 8, 9. So general solution is CF plus PI. Y is CF plus PI. D square plus D plus 1, we have already done it. Its roots are complex. You have to write the complex roots. Okay. Now let me take one more question. D square minus 2d plus 4 operating on y equal to e raised power x cos square x. Now auxiliary equation, you will do it yourself. I will show on the particular integral. E raised power x cos square x d square minus 2d plus 4. What you are supposed to see or find particular integral. So e raised power x out, replace d by d plus a. A is 1 here. It is d plus 1 square minus twice d plus 1 plus 4 operating on cos square, which is e to the power x 1 upon d square plus 2d plus 1 minus 2d minus 2 plus 4 operating on cos square. Okay, let me not, we don't know anything about cos square, cos cube, sine cube, but I have shown you how to find sine cube. So cos square is cos into cos, or it is 1 plus cos 2x by 2. Okay, because we know 1, how to find the particular integral of 1, because 1 is cos 0 is 1, or you can write e raised power 0x, it is also 1. You can use any method. So 2d and 2d goes. What remains is e raised power 2x, e raised power x, 1 plus d square, 4 5 minus 3 plus 3 operating on 1 plus cos 2x by 2. Fine. Now this is equal to e to the power x by 2. Let me take 2. This 2 is here, divided by 2. This is 1 upon d square plus 3, then cos 2x upon d square plus 3. Okay, now 1. You can replace 1 by e to the power 0x, and in that case, when it is e to the power ax, you are replacing d by a. So e to the power x by 2, a is 0, so 1 upon 3. Then d square by minus a square, a is 2, so a square is minus 4. So cos 2x minus 4 plus 3. So the solution is e raised power x by 2, 1 by 3 minus cos 2x. Fine, this is the particular integral. So general solution is complementary function plus particular integral. Okay. So every question can be solved in this form if you have a product of two functions. But then if you have a question of this type, say you have a question d square minus 3d plus 2 operating on y equal x sine x. See, these are product of two functions, x and sine x. How will you do it? You cannot, or it is x into cos. There is no e raised power ax here, over here, right? So how to find it? Now you know the roots. Its roots are 1 and 2. You know it. M square minus 3m plus 2 means m equal to 1 and 2. D minus 1 and d minus 2. I will just give you a hint how to solve such questions. Otherwise, you will do it yourself. See, whether it is sine or cos, two things will be there. Either a polynomial and to sine, polynomial into cos. If it is e raised power x, there is nothing to worry about because I have already shown you how to find the solution of such type of questions. Now, sine or cos, what you will do? Complementary function, leave it particular integral x sine x upon d square or d minus 1 d plus 1 d minus 2. Fine. Now what is the procedure? Sine, whether you have sine or cos, you know e raised power ix, it is cos x plus I sine x. So if you have sine x over here, you will take the imaginary part of e raised power ix. If you have cos x over here, you will take the real part. If it is sine 2x, e raised power I 2x. It is sine 3x, e raised power I 3x. Cos 5x is the power I 5x, real part only. But for sine, you have to take imaginary. So I can write this question as, this is imaginary part of, see, x e raised power ix, d minus 1, d plus 1, d minus 2. Okay. Now, what is the method? Leave this imaginary part. You have now this question. X e to the power ax means e to the power ax into some function v, where v is a polynomial. Okay. So, this is imaginary part of. You need not write this question in this form, d minus 1, d minus 2. You can put it in this form also. Ix e to the power ix upon d square minus 3d plus 2. Doesn't matter. If you want to keep it like this, okay. If you want to keep it like this, what is the method? Okay, let me write it in this form so that you will not be confused. Because you have fd over here, d square minus 3d plus 2. D square minus 3d plus 2. Now, imaginary part, leave imaginary part. You have the question, this one is the question. E raised power ix 1 upon d square. Okay. x. See, I will use the formula e to the power ix into v. This is v. And what is your a? It is iota. So this is e to the power ix as it is. This is 1 upon d plus iota whole square minus 3 times d plus iota plus 2 operating on x. Now this is fd operating on x. X is a polynomial. You know what to do. You have to take lowest degree term out. You can simplify it or you can write it as it is. What is the lowest? This is imaginary part of e to the power ix. You have taken 2 outside. It is power ix by 2. What remains is 1 plus d plus iota whole square minus 3 d plus iota by 2 operating on x. Is it okay? You see, you have to take 2 outside. What will remain is 1 plus some function of d divided by 2. 1 plus some function of d divided by 2. Now you are taking it to the numerator. So this is raised power minus 1. This is what we are doing for polynomials. You know, you have to take lowest degree term outside. This will be 1 plus minus some function of d. 1 plus minus some function of d. Now take it to the numerator. This is numerator. Now you can expand it. And you know, this is x only, so you are taking d only. You don't have to take d square. So imaginary part of e to the power ix by 2, 1 plus, see this is d square, you don't have to take that. Then iota square, okay. Then 2d plus 2di. Then iota square, let me, okay, wait. This is 1 plus d square plus iota square plus 2di. Okay, this is 1 minus 3d plus 3 minus 3i plus, now it is square. This will be again this square plus this 4, so on. We will not take further terms operating on x. Now this is 1 into x. Then d square into x, you don't need to, those I square is minus 1, so minus x. Then 2 iota differentiation of x is 1. Then 3 differentiation of x is 1. This is minus 3 iota. Minus 3 iota into x. And so on. Maybe I have chosen few, I just want to show you what to do. Now this is some real part and imaginary part. This is cos x plus I sin x. And this is real part. What is the real part? X minus 3 plus iota times 2 minus 3i. 3x. Okay? Whatever the imaginary part will be there, you will get the answer. What is the imaginary part? You see, this is iota sin x. Sin x into x. This one into is this. Then, wait. Okay, this is okay. Then this is iota. This is iota cos 2 minus 3x. Minus 3x into cos. See, this is iota into this. The rest will be this one real. Then this iota into this cos. This will be imaginary. So this is the answer. There is one shortcut method also. Let me not show that to you, or let me quote it. Shortcut method is that if you have x into v, you don't have e to the power ax into v and fd. This is equal to x v upon fd minus fd dash upon fd square operating on v. Operating on, yes, operating on v. See, we were having right hand side x and sin x. As per this formula, this will be x. What is your v? It is sin x upon fd. That was fd was there. Minus derivative of fd. Then let me write it down. What was it? It was d square plus. I don't remember what I had taken. Question. What was the question? D square plus d plus 1, I think. Yeah. Okay. Now derivative is two d plus 1, then d square plus d plus 1 whole square operating on sin x. X v with sin x upon d square plus 1 whole plus 1 minus derivative of fd 2d plus 1, and then this is square operating on sin. So this is quite easy. You have to replace d square by minus 1 and here d square by minus 1 and operate. Okay. Now let me come to linear differential equation with variable coefficients. This is all about linear differential equation with constant coefficients. Okay. I will be now taking up linear differential equation with variable coefficients. Linear differential equation with variable coefficients. See, a linear differential equation with variable coefficients is a differential equation of the form x raised power n, nth derivative, x raised power n minus 1, n minus 1th derivative, x square, second derivative, x first derivative, plus some constant, say y is equal to some function of x. See this is x raised power 0, you can take. Remember linear differential equation with constant coefficient, it was same except x raised power n, it was a raised power n minus 1, a square, a1 and a0. Here it is x raised power n minus 1, x square, x and x raised power 0. So instead of constant coefficient you have variable coefficients. And one more thing is that with other derivative you have x raised power n. With n minus 1 derivative you have x raised power n minus 1. Homogeneity is there. With d square you have x square. With d you have x, y is alone and x is function of x. It can be any function. Now how to solve such type of equations? So this equation has symbolically we can write it as this: x raised power n, d raised power n, x raised power n minus 1, d raised power n minus 1, x square, d square. Just like linear differential equation with constant coefficients. Okay, now how to solve such type of equations? See, what is the method? Method is that we first transform a linear differential equation with variable coefficients into a linear differential equation with constant coefficients. When this is reduced into a linear differential equation with constant coefficients, we have nothing to worry about, because we know how to solve a linear differential equation with constant coefficients. Okay, so the task is that we have to reduce a linear differential equation with variable coefficient into a linear differential equation with constant coefficients, and the solution is known to us. Now, how to do that? What is done is that we put x equal e to the power z. This gives us z is equal log of x, so that dz by dx is 1 by x. Fine. Now, first of all, what is this d? This d is d by dx. You know, this was in linear differential with constant coefficient also, and this in linear differential with variable coefficient, this is d by dx. Because d is d by dx. Now, because I will be using d1 or d dash or dx or dy, whatever the case may be, you will see different notations in different books. So I will be using d1 over here instead of d. And what is d1, you will come to know. Now, this is okay. I have put x equal e to the power z. This gives us z equal log x, which gives us dz by dx is 1 by x. Fine. Now I want to find dy by dx. Now, dy by dx, what is that? Dy by dz, chain rule, dz by dx. Fine. But dz by dx is 1 by x. So this is 1 by x, dy by dz. So I have dy by dz dx. Derivative of y with respect to x is nothing but 1 by x. Derivative of y with respect to z, when I have chosen x equal e to the power z. This is 1. Now let me differentiate it again with respect to x. What I will get? d2y dx2. Now this is the product of two functions. Okay? Product of two functions. What is differentiation of 1 by x? It is minus 1 by x square dy by dz. Then plus 1 by x. Okay, d by dx of 1 by x, d by dx of dy by dz. Okay? You have two functions, 1 by x and dy by dz, and you are differentiating with respect to x. So derivative of 1 by x, this is u, 1 by x square minus 1 by x square dy by dz as it is. Then 1 by x as it is, d by dx of this. This is okay. Fine. Now this can be written as minus 1 by x square dy by dz plus 1 by x. Now see here. This is d2y dz2. I have to differentiate with respect to z. Sorry, x. But x is function of z. So I have differentiated with respect to z first, and I will differentiate z with respect to x. Fine? I have to differentiate with respect to x. X is function of z. I am differentiating with respect to z first. d2y dz2, and I am differentiating z with respect to x. Fine? This you know, this is in 12. Now what is dz by dx? dz by dx you have seen. It is 1 by x. You know, this is z equal log x. So dz by dx is 1 by x. You have seen this. So this is minus 1 by x square dy by dz plus 1 by x square, because dz by dx is 1 by x, d2y dz2. Or this is, see now, see here first. This gives us x dy by dx is dy by dz. Okay, this is one, not this one. And here you will get x square d2y dx2 is minus dy by dz plus d2y dz2. You have taken 1 by x square out. X square is here. See, this is nothing but, let me write over here. This is d1y. What is d1? D by dz. This is d by dz. I am writing it as d1y. Fine. Now, as per this is d1 minus d1 square plus d1 square operating on y. Or this is d1 into d1 minus 1 operating on y. See, this is d1. This is d1 square. So this is d1 into d1 minus 1. Similarly, you can prove, you can show what? X cube d3y dx3 is d1 minus 1, d1 minus 2, and so on. X4 d4 will be d1 minus 2, d1 minus 2, d1 minus 3, d1 minus 1, d1 minus 2, d1 minus 3. X5 it will be up to 4, x6 it will be up to 5, and so on. So what I have seen that this is d, right? So in short, thus we have seen what we have seen. X dy by dx, which is x dy. You see, this is x dy. This is d. Is d1y, and your d1 is d by dz. X square is x square d square. It is d1 into d1 minus 1. X cube d cube y. It is d1 minus 1, d1 minus 2, y, and so on. This I have seen, and I will be using this in order to transform a linear differential equation with variable coefficient into a linear differential equation with constant coefficient. Question number 1. I hope you understand this. X square d square minus 7xd plus 12 operating on y equal x cube. X square d square minus 7xd plus 12 operating on y equal x cube or x square. Let me write x square first. You can write x cube, x4, x5, whatever you like. This is what is the question actually? Question is that x square d2y dx2 7x dy by dx plus 12y equal x square. This is the question. X square d2y dx2 minus 7x dy by dx plus 12y equal x square. Now, put x equal to e to the power z. You see, now I will get only one question. I should get that why do we put x equal to e raised power z? This is a problem to you. You will have to answer this, not me. Why do we put x equal to e to the power z? See, so in order to transfer a linear differential equation with variable coefficient, let me put x equal to e raised power z. This gives us z equal log x. This gives us, and therefore x dy is d1y, x square d square y is d1 into d1 minus 1y. You don't have x cube, you have only these two. This I have shown, I will be using this, but if you are in an examination and you are asked this question, you have to put x in, you have to show that x dy by dx is d1, x square is d1. Okay, now let me use it over here. Therefore from 1, hence from 1 we have x square d square, x square d square, it is d1, d1 minus 1 y minus 7xd, it is d1 y, I have not taken y, plus 12 y equal x square. You see, your x is e to the power z. What is x square? It is the e raised power z whole square, it is e to the power 2z. So e raised power 2z. Okay. Now this is what? d1 square minus d1 or minus twice d1. Chalo, d1 minus d1 plus 12 operating on y equal e raised power 2z. Or finally I have d1 square minus 2d1 plus 12 operating on y equal e to the power 2z. Now I will not go auxiliary equation. I will not find the complementary function. This is now okay. No. Let me find. Oh, why I have written this was 7, na? This was 7. Hello. Your question was like this. Question was x square d square minus 7 xd plus 12 operating on y. So this is minus 7x. 8, this is minus 8. Hello. X square d square minus 7xd plus 12. If it is minus root, doesn't matter. You will get complex roots, doesn't matter. So it is 7. So minus 7 d, and you have 1 d, over here. So 7 and 1 is 8. So 8 even plus 12. Now auxiliary equation. M square minus 8m plus 12 equals 0. Same. What's m? Minus b plus minus 64 minus 4ac. 48 by 2. So it is 8 plus minus 14, 18. It is 6 and 1, 16. So it is 4 by 2. Okay? 6 and yes, it is okay. Now m is what? It is 8 minus 4 by 8 minus 4 is 4 by, it is 2. And 8 plus 4 is 12, is 6. So complementary function is, here you have to see, that's why I have taken complementary function, otherwise you could have done it of your own. Complementary function is c1 e to the power x or z. Z, because your d1 is what? Your d1 is d by dz, not x. So it is 6 e to the power 2z. Then c2 e to the power 6z. Fine. But what is z? X equal to e raised power z. So what is z? Z is log x. So this is c1 e to the power 2 log x. c2 e to the power 6 log x. So this is c1 x square, you know, or c1, okay, let me write one more factor, one more term, c1 e to the power log x square, c2 e raised power log x raised power 6. So this is c1 x square plus c2 x 6, because my original differentiation was in terms of x and y, x square d square x 7xd and so on. So my complementary function as well as particular integral should be in terms of y, in terms of x, not in terms of z. This is the conversion only. So I have, this is the complementary function in terms of x. Now particular integral. Pi e raised power 2z upon d1 square minus a d1 plus 12. Now what is the rule? Rule is that you have to for e to the power ax upon fd, you have to replace d by a. So a is 2 over here. So it is e raised power 2z. 2 square it is 4. 2 8 16 plus 12. So particular integral is e to the power 2z divided by, oh, this is a case of failure. You see, 12 plus 4 it is 16 minus 16 is case of failure. So what is the method? Case of failure, huh? So this is e raised power 2z. You have two factors. What are the factors? D minus 2 and D minus 6. Not D, here you have D1. D1 minus 2, D1 minus 6. This is D1. Now, this is the factor which doesn't vanish, and this is the factor which vanishes. So you have to substitute over here, not over here. So this is e to the power 2z. 2 minus 6, D1 minus 2. So my particular integral is e to the power 2z. See, this is minus 4. Now this is e raised power 2z upon d1 minus 2. You have to replace d by d1 by 2. This is a case of failure, so you have to multiply by x. Okay? If you don't, let me, if you have not understood, this is minus 1 by 4. E to the power 2z upon d1 minus 2. This is a case of failure, so I have to multiply by x. So minus x by 4 e to the power 2z. Now, this is your complementary function. The particular integral is in terms of z. Not हो एक और चीज है. See here. This is in terms of z. So you have to multiply by what? Not in terms of x, in terms of z only. This is z. You see? It was e to the power ax upon d minus a. It is not e raised power ax. It is e raised power az upon d1 minus a. So you have to multiply by z. If it is d minus a whole raised power r or d1, then it is z raised power r by factorial r. Remember it once for all. So this is z. But what is z? Z is log x. So let me write it in terms of x. So minus 1 by 4 log x and e raised power z square. It is e raised power 2 log x. So particular integral is minus 1 by 4. This is x square log x. And your general solution, complementary function plus particular integral. It is c1x square c2x6 minus 1 by 4 x square log x. Fine. This is a linear differential equation with constant coefficient. What we have done, we have transformed a linear differential equation into a variable coefficient into a linear differential equation with constant coefficients and proceeded. One more question. X square d square minus 3xd plus 4 operating on y is cos of log x. X square dx minus 3xd plus 4 operating on y equal cos of y log x plus some say plus x square also. How does it matter? Okay. Or plus 1 by x plus 1 by x. You can, after thorough practice, you can form your questions of your own. So let me transform this. You have x equal to e to the power z, and you know x square d square is d1 minus 1. 3. xt is d1 plus 4 operating on y equal cos of log x. You see, log x is z, cos of z. 1 by x is e raised power minus z. Fine. You see, x is equal to e to the power z, means z equal to log x. And since x is 1 by x, x is e to the power, this is e raised power minus z, which is e raised power minus z. This I have used. Now this is what? d1 square minus 3d1 plus, so minus 4d1. This is d1 square minus d1 minus 3d1. So minus 4d1 plus 4 operating on y equal cos of z plus e raised power minus z. Auxiliary equation is m square minus 4m plus 4 equals 0. M minus 2 whole square equals 0. M equal to m2. Complementary function. C1 plus C2 z, not x. E to the power 2z. Fine. C1 plus C2 z e raised power 2z. Now particular integral. Particular integral is cos z e raised power minus z divided by d square minus 4d plus 4. Okay, or d minus 2 whole square. d1, not d. This is cos z upon then e raised power minus z upon d1 square minus 4d1 plus 4. So cos, you have to replace d square by minus 1. Cos z minus 1 minus 4d1 plus 4. Then e raised power minus z, d1 by minus 1. Minus 1 square is 1 plus 5 plus 4. So cos z 3 minus 4d1 e raised power minus z by 10. Now rationalize it. This is 3 plus 4d1 cos z 9 minus 16d1 square. It is 3 cos z 4d1, d differentiation is sine, upon d square is minus 1, so it is 25. So complementary function, it is c1 plus c2z e raised power 2z plus particular integral 3 cos z minus 4 sin z divided by 25. Is it okay? This is okay. I have not written this. E raised power minus z by 10. Okay? Complementary function plus particular integral. This is particular integral. Now this is in terms of z. But you know this, your answer should be in terms of x. So you will replace z. So this is complementary, y. Y is equal to C1, C2, yes, what is Z? X is e to the power Z. Z is log x. So C1, C2 log x, e raised power 2Z. E raised power 2Z is log x, so it is x square plus 3 cos of z means cos of log x minus 4 sin log x divided by 25 plus e raised power minus z. e raised power minus z is 1 by x. This is the solution. Okay, you have to replace z everywhere. You can do it in the middle part or you can do it at the last. That's why I have shown this in the last. Now let me take one more question. Before that I will put on the light. Okay, some light is there now. Okay. X square d square minus xd plus 1 operating on y equal log x by x whole square. See, I will not show it completely. Okay, I will be taking you to some path and then after that you will be doing it. This is d1 minus 1 minus d1 plus 1 operating on y equal, you see, your x is e to the power z. So log x is z. So this is z, log x is z by e raised power z whole square. Fine? Okay. So you have d1 square minus 2d1 plus 1 whole raised power y equal e raised power minus 2z into z square. This is quite easy now. You have d minus 1 whole square or d1 minus 1 whole square operating on y equal e raised power minus 2z z square. Auxiliary equation is quite simple. You will do it. Particular integral, for particular you have to replace d by d plus a, right? Or you want me to show auxiliary equation again? This is m equal to 1 and 1. Complementary function is c1 plus c2z e raised power z. Fine. Particular integral e raised power minus 2z z square upon d1 minus 1 whole square. This is e raised power minus 2z. Replace d by d plus a. A is minus 2. d1 minus 2 minus 1 whole square operating on x square. Sorry, z square. So this is e raised power minus 2z 1 upon d1 minus 3 whole square operating on z square. Now which is the lowest? This is a polynomial now. Polynomial. For polynomial, what are we doing? We are taking lowest degree term out. So e raised power minus 2z. Lowest degree term is minus 3. Minus 3 whole square is 9. This is, now let me take it to the numerator. 1 minus 3 upon, sorry, d1 upon 3 raised power minus 2z square. This is it. You have taken 3 outside. This is 3 square, which is 9. Then 1 minus d1 by 3. Minus you have already taken, which is plus. So 1 minus x raised power minus 2. Use binomial expansion. You will get the solution. This is 1 plus 2 d1 by 3 plus 3 d1 by 3 square plus so on operating on z square. You can differentiate only up to z, up to d square or d1 square, not beyond that. So this is e raised power minus 2z by 9. 1 plus 2 by 3. Differentiation of z square is 2z. And this is z square over here, 1 into this. Then 3 by 3 square. So it is 1 by 3 only. d1 square. First derivative is 2z, second derivative is 2. And rest goes. This is it. You can simplify it and transform it in terms of x. I hope this you understand this. There will be some, you see, I am just hurrying. There may be some mistakes over there and here, but the method is okay. This is the method you have to follow. Next, let me take last one. Let me take, say, x cube d cube 2x square d square plus 1 operating on y, x plus 1 by x. Okay, x cube d cube, x cube d cube, because your homogeneity should be there. X cube d cube, then 2x square d square plus 2, let me write 2, operating on y equal x plus 1 by x. Okay, see, x cube d cube, what is that? d1 minus 1 d1 minus 2. Okay, then 2 x square d square d1 minus 1, then 2 operating on y. Your x is e raised power z, 1 by x is e raised power minus z. Fine, this is it. This is, let me find it out. This is d1 square minus 2d1 minus 3d1 plus 2. So this is d1 cube 3d1 square plus 2d1. d1 square minus 3d1 plus 2. So this is d1 cube minus 3d1 square 2d1 plus 2d1 square minus 2d1 plus 2 operating on y equal e raised power z plus e raised power minus z. So this is d1 cube. Now how many d1s? Minus d1 square now plus 2 operating on y e raised power z e raised power minus z. Now this is an auxiliary equation, you can find it. 1 minus 1, we'll do it, huh? Particular integral is e raised power z plus e raised power minus z d1 cube minus d1 square plus 2. Okay, huh? Do it. Okay, with this I come to this end of this lecture. Let me take some more examples in the, or this is okay, this is fine. What we have to do is that we have to reduce a linear differential equation with constant coefficient into a linear differential equation with variable coefficients. We have to reduce a linear differential equation with variable coefficient into a linear differential equation with constant coefficients by taking this substitution x equal to the power z. Okay, thank you.